We're continuing with applications of integration in Chapter 6. In this video, we're going to go through Section 6.4, which talks about work. And so, as we've talked about the different applications of integration, we started with areas between curves, which was like an extension of the area under the curve. Then we talked about volumes. Then in Section 6.2 and 6.3, we extended the idea of integration or infinite summing past just areas, and we thought about volumes. And so now in Section 6.4, we're going to take another step into looking at the idea of integration or infinite summing from another angle. So it's going to be different than areas, different than volumes, and you'll see how it's different as we go through this section. Okay, and so as we go through this section, for the entire section, we are going to be strictly talking about integrating to find the total work done in a process, and we'll talk about what work means in a second. But as we go through this, just note that it's not so much about work. So work is something that you learn in physics, okay? But this isn't a physics class, so it's not so much about work as just they want to illustrate an integration process. So any other function or any other, parameter in business, chemistry, engineering, etc., you can integrate in the exact same way as what we're about to outline here, assuming the behavior is similar. So as we go through this section, just try and focus on the process of integration, how we're integrating to find values of this parameter, this work parameter here. So really try and focus on the mathematics that's being done as opposed to the concept from physics called work. Okay, the term work is used in everyday language to mean the total amount of effort required to perform a task, right? That's what you think about, just the general term work, right? That's what you think, that's a general definition for the term work. How much effort was required to do something. In physics, however, it has a technical meaning that depends on the idea of a force. So work in physics depends on the idea of a force. What is a force? Intuitively, you can think of a force as describing a push or pull on an object. For example, a horizontal push of a book across a table, or the downward pull of the Earth's gravity on a ball. In general, if an object moves along a straight line with position function S of t, then the force F on the object in the same direction is given by Newton's second law of motion as the product of its mass, m, and its acceleration, a. All right, so again, don't get too bogged down with trying to, this isn't a physics course. Don't get so bogged down with trying to understand the exact physics here. But we're going to be looking at the process of integration to find what's called work here. And in physics, the amount of work done is directly related to forces. And so they first wanted to define what a force is. Okay, and so they give a definition that you kind of intuitively understand what a force is, right? It's like a push or a pull, like gravity exerts a force on objects, pulling them down towards the center of the earth. You can push on a car, things like that. And force from a quantitative standpoint was developed by Isaac Newton, and this is exactly what's still used today in like engineering, engineering mechanics. They still rely fully on this is Newton's second law, and which says that the force on an object is equal to the mass of the object times the acceleration of the object. Now, this might be a little confusing because you think about, well, I can like push on a wall and the wall is not moving, but the wall still has a force on it. And so again, this isn't a class in engineering mechanics, but the idea there, that's what's called engineering statics. And yes, the wall isn't accelerating, but if you like separated the wall out into empty space and you drew all the forces acting on it, so you pushing on the wall and then all the other forces that are resisting the wall from moving, then due to all of the forces acting together, the wall wouldn't be accelerating, but you could still have a group of forces acting on something, but that something is not accelerating. So the sum of the forces are equal to zero, but there's still forces acting on it, like a building, right? A building isn't moving, but there's still obviously forces acting on it. Okay, but then if you do like an analysis of all the forces on an object and you know that object is accelerating, then the sum of all the net sum of all the forces will be equal to the objects. It won't be equal to zero, like in the statics case, like if you were doing like a bridge or a building, it would actually be equal to the mass of that object times that object's acceleration. Okay, so just trying to give you a little bit of context here. This is not an engineering mechanics course. Now, another thing to note here is that this is a simple case that we're looking at where an object is moving along a straight line with position function s sub t. So this is a simple case where we have a position, the position is a function of time, and this is just a straight line motion. So what is straight line motion? Here's 0, the origin. That means this object can move in the positive direction. And this line could be vertical, whatever, just straight line motion. This is the positive direction or the negative direction. So this S can be positive or negative. The velocity can be positive or negative depending on if you're moving to the right or to the left. The acceleration can be positive or negative depending on if you're accelerating in the positive or negative direction. Okay? Now, when you have a position function, S sub t, then according to Newton's second law, if you want to find the force on this object, then you can take the derivative of the position function twice, because you take the first derivative, you get the velocity. You take the second derivative, you get the acceleration. So the force is equal to, if you're assuming the mass of the object is constant with respect to time. So like a rocket shooting up into space as it's leaving Earth, the mass isn't constant, right? It's losing all the mass of the fuel that's burning. But most of the time, the mass is constant. So in that case, you have to have m as a function of time as well. But so m is constant for this object times the acceleration, which is based on the position function. Okay? In the SI metric system, the mass is measured in kilograms, the displacement in meters, the time in seconds. So yeah, for these units, a Newton, if you're using, for MA, if you're using kilograms, meters, and seconds, then you get, that's what a Newton is equal to. 1 Newton is 1 kilogram meter per second squared, right? Kilogram meter per second squared. That's the units of M times A. Thus, a force of 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second squared. In the U.S. customary system, the fundamental unit is chosen to be the unit of force, which is the pound. So I'm not going to get into how U.S. units work with Newton's second law. In the case of a constant acceleration, the force F is also constant, and the work done is defined to be the product of the force F and the distance d that the object moves. So, yeah, what they're saying here is that if the acceleration is constant, and then if the mass is constant as well, which most of the time it is, and that's what we're assuming here, then this simplifies to where you just have this. F is equal to ma, and so what they're saying, in that case, then if you want to find the work done on an object, it's the force times the distance the object moves. Okay, now this is the simple case where the acceleration is constant. And so what does that mean? Since the acceleration is constant and the mass is constant, the force is constant. So you just say that constant force times the distance. That's what work is. The energy, it's like an energy transfer to an object, a mechanical energy. It's the force acting on that object times over the distance that object moved, with that force being applied. That's what work is. And again, don't just try not to get bogged down with the engineering here. But what if the force isn't constant over the distance, right? So maybe the acceleration isn't constant. That's where integration is going to come in. Like you want to calculate W, but the force isn't constant. All right, if F is measured in newtons and D in meters, then the unit for W is Newton meter. A Newton meter is called a joule. If F is measured in pounds and D in feet, then the unit for W is foot pounds, which is about 1.36 joules. Okay. Example 1. How much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? Use the fact that the acceleration due to gravity is 9.8 meters per second squared. And so what happens here is that the weight of objects is constant because of this comes from Newton's law of gravity, because the Earth is so enormous compared to all objects on the Earth that, the weights are constant. And so whenever you pick the book up, and you put it on the desk, the force is constant, right? The weight of the book doesn't change. Now, there might be dynamics that come into play where, you pick up the book and then it accelerates in the beginning and then decelerates, but we're looking at just simple cases here to illustrate the concept of integration for like a parameter, okay? And so you just get the weight of the book, so that's 1.2 times 9.8, 1.2 kilograms times 9.8, and then the distance. Now, the distance here, it's important to note, it's not like a horizontal distance, okay? They're just talking about the work. It's the vertical distance because it's the distance in the direction of the force. It's force times the distance in the direction of the force. And so this is like a really simplified case just to illustrate the concept, but we're not going to, in this section, we're not going to be looking at examples of what do we do if the distance is in the force vector direction and the distance vector direction are different. We'll look at something like that in Calculus 3. But right now we're just thinking about the force times the distance, but they're both in the same direction. So that would be, it would be the distance. That's why they specify here 0.7 meters high. And again, I'm just trying to teach you the engineering of this just to give you some context. That's the only reason. Give you the context you need so you can understand the math. So they're saying 0.7 meters high because, and they want to specify high because it's the work we're calculating is the force times the distance where they're both in the same direction, right? So if you lifted up the book from here onto this desk and it went like that, onto the desk, well, the force due to gravity, the weight is acting down. So you're not going to say this force times this distance. You're going to say this force times this distance. And the force is constant. So so it's easy. Force times distance, the constant force times the distance. And that's it. And then part B, it says how much work was done in lifting a 20-pound weight 6 feet off the ground. Well, yeah, now it gives us the weight. We don't have to we don't have to multiply 20 times 9.8 because it gives us the weight already. Okay. Now, so what we just did was it was simple because the force was constant. And I mean, this would be if you calculated the work done this way, you could assume the force is constant, even though, like you pick it up and it accelerates in the beginning and decelerates in the end. That would still be a good assumption because, the weight of the book is constant. So you get an accurate answer for the work done in lifting that book off the ground. But then there would also technically be work done to accelerate, to push the book to the left and accelerate it, against its inertia. But the work done in this sense, going from right to left, wouldn't be associated with gravity. So only thing you're calculating here is the work done against, in relation to gravity, in relation to the weight of the book to put it on the desk. But yeah, technically there would be some work done to push the book, to accelerate the book from right to left. But again, this is a simple case to illustrate the integration of a parameter concept. So what we just did was we assumed that the force was constant, right? The force due to gravity. But what happens if the force is variable, right? So that wouldn't be the case here, but what if the force over the distance, there's a force acting on something over a distance, but what if that force isn't constant over that distance? Let's suppose that the object moves along the x-axis in the positive direction from x is equal to a to x is equal to b, so that's straight line motion. And at each point x between a and b, a force f of x acts on the object, where f is a continuous function. Okay, so we're going from, what they're saying is, it's the straight line motion, and we could start in the negative, at a negative position. It doesn't matter. So let's say we're starting here and ending here, and so this object is going from a to b, x is equal to a to x is equal to b, and for all positions of the object between a and b, we know we've got a function, a force function, a function of x, right? This is x. Okay, now just notice though, this is not f of t. This is not the force as a function of time. Like we're talking that we have a function that for the force is a function of the position x. And also just notice that you can have like negative work done. So if the force, how would negative work be done? If the force direction and the position direction were different. So if like the object was moved from here to here, but the force was in the opposite direction as it moved from here to here, then that would be negative work done. So that would like subtract from the total work done, right? Like you could imagine like from going from A to B, it's like a net work done. Some you have positive work, but then there could be some negative work that subtracts from that. All right, so we've got this force as a function of x. So how do we calculate the work done? With this variable force. We divide the interval AB into n subintervals with endpoints. Okay, so look, this is the definite integration process. We're dividing the interval from A to B into these n subintervals with endpoints at the right endpoints, right? That's how we set up the integration. We set it up. We separate the independent variable into n subintervals, and the endpoints of the subintervals are x0, x1. Well, yeah, these are just the endpoints actually. These are the endpoints, but the way it's set up is that like x of 1, that's the right endpoint of the first interval. X of 2 is the right endpoint of the second subinterval. That's the way this is set up, with equal width delta x. We choose a sample point xi star in the ith subinterval, right? So that's xi star is any point within each subinterval. Then the force at that point is f of xi star, right? You can pick up, this is within each subinterval, if you can pick the right endpoint, the left endpoint, the midpoint, whatever, and that's kind of like you could look at it as the force within that subinterval. But the idea is if n is large, then delta x is small, and since f is continuous, the values of f don't change very much over the interval. So, if n gets large, then you can look at this function, this force function, no matter what position at xi star. If you assume that whatever force, whatever position you choose, left endpoint, right endpoint, whatever, it's a good assumption that you can say that force is constant over the interval as n gets large. And then furthermore, as n gets large, it doesn't matter if you pick the left endpoint, the right endpoint, the midpoint. And so how could you assume it's constant? What does that mean? Well, that's the whole idea of the integration with you're making these rectangles. That's what we've always done with every integration that we've done up to this point, and that we're ever going to do. That's what we've assumed, that the function is constant over the interval, right? That's the whole idea. You're integrating an area under a curve, and you're assuming within a interval, you're assuming that the value of the function is constant over that interval. That's the whole idea, right? This is the right endpoint. You see, that's what we do, right? We evaluate the function at some point within the interval, and we assume that the function is equal to that value over the entire interval. That's the integration process. And then when n gets large, that assumption of a constant value within the interval becomes a very good assumption, a better and better assumption. And then furthermore, the point that you choose to be that constant value, the x point that you evaluate within the interval, doesn't matter as n becomes large, in particular as n goes to infinity. And so what they're saying is that, in this case then, you can calculate the work done within any interval as it's approximately equal to f of xi star delta x. And then so you can turn that into a Riemann sum, and you get, here's an approximation for the work done. So an approximation, because this is just, you can pick an n here. N is equal to 10, n is equal to 20, etc. And then, what you would do is, it says it seems that this approximation becomes better and better as we make n larger. They don't draw a diagram here, but this is an important part of developing an integral. So you develop the Riemann sum like we just did. So if you were doing this from scratch, you would have to think about, okay, this parameter of work, can I think about the idea of breaking this parameter up that I'm trying to find into these pieces, and then summing those pieces. And so so what we did was we defined this straight line motion here with you have displacements along this straight line in the positive or negative direction, and you have forces acting on the object either only in the positive or negative direction. And we thought about the idea of, okay, so we're trying to calculate, it's like force times distance, but the force is variable. But if we have a force, this continuous function that represents the force on the object as a function of its position, then can we think about the idea of dividing the x-axis into these small equal width pieces and assuming the force is constant over those independent variable piece widths? And it makes sense. That does make sense, right? Because if you've got force as a function of position, and we're going from A to B, so we've got this continuous function here. Okay, well, what are we trying to do to get the work done? We're trying to get the area under this curve, right? We couldn't see this diagram when we were just looking at it from like a displacement chart, displacement of the object. We couldn't see like area under curve. But if we draw it this way, we have this force as a function of x, then the area under the curve between A and B, that's the work done, right? Because why is that? Because what you're trying to do to get the work is you're just trying to get the force times the position. But when the force is variable, to do that, you have to break, you want to break this up into these small pieces. And then as those pieces get small enough, you can assume that the force is constant over that piece, the width of that piece, right? And you would use the midpoint rule. You can think about, for the approximation standpoint, you would use the midpoint rule. And that would get a better approximation. But as n goes to infinity, it doesn't matter. Right? I mean, this is the area under the curve. So we know areas under the curve works with integration. So this is completely valid here. This Riemann sum, as n gets larger and larger, this converges to like something that we can define to be the exact value for the work done on an object that's moving over a distance with a variable force acting on it. So we define the work done in moving the object from A to B as the limit of this quantity as n goes to infinity, right? So you take the limit as n goes to infinity here, and you can turn this into an integral. So they take the limit as n goes to infinity here. That's the work done on an object, and here's the integral. So what they're saying here, we're just talking about straight line motion, which is a very simple case, just for illustration of the concept. So just straight line motion. Straight line motion. The work done on an object, if you have the force acting on that object as a function of position, then you can integrate from x is equal to A to x is equal to B, the force function dx. And that's the work done. Okay, and again, you can have negative work done. Like this is like, right, then a definite integral it's like a net area under a curve. So if you're thinking about f of x, it's a net area under the curve, right? So you can have like positive work done here. Now you're subtracting work, and all that is, what they're saying there is that if you have positive work done, then you're accelerating the object, like you're adding energy to the object. The object's like that. That's what's happening. If you have a force acting over a distance, then you're accelerating the object. But then here you'd have the force acting in the opposite direction of the motion. And so you're slowing the object down, is what's happening. All right, so it says in this example, it says when a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x is equal to 1 to x is equal to 3. So, yeah, so they just have this is a force function. It's a function of position, right? Here's 0. It's a straight line motion. Here's 0, and this is positive x. And so this could be x feet in the positive or negative direction from the origin. It doesn't matter. They're saying this is the function for the force. At any position x, positive or negative. But then what's the work done in moving it from x equal to 1 to x equal to 3? You just integrate that. Okay, and so, again, I keep saying this. I'm not, this is not a physics course, an engineering course. They're just trying to illustrate the idea of integration, the infinite summing from different angles. That's what we're doing in this chapter. And so one way you can look at this is if you've got a problem in business or chemistry or biology, engineering, and there's a parameter that, in very simple terms, is just is equal to the multiplication of two parameters. It can be more than two parameters, but this is single variable calculus at the moment, so you'd have to be able to, if it was more than two, okay, well, let's just say it's two parameters at the moment, then if one of those parameters for the non-simple case was variable, then you could still find the value of the main parameter with integration if you can represent that variable parameter as a function of the other parameter. Now, if you have more than two parameters that are being multiplied, then you'd have to have one of the parameters be like an independent variable, and then the other more than one parameter would be like you have to have as a function of the independent parameter. You see, like if you had this L is equal to X, Y, Z, then you have to treat like Z as the independent variable, and you have to represent both X and Y as a function of Z. You'd have to represent it as one dependent variable that's a function of the independent variable. Then you can turn it into the idea of finding an area under the curve, right? You turn this into some function of Z times Z, and then to get, well, no. Yeah, you would turn this into some function of Z, and then, so you have a function of Z times Z, so this whole thing would be a function of Z, right? And so you'd have L of Z. So L would be the dependent variable, and then you have some expression of Z, and so that's what you'd be doing. You'd be finding the area under the curve of this function of Z, you see? And this might seem far-fetched, but we're just learning single variable calculus at the moment. You'll have a lot more versatility once you learn multivariable calculus, but it's still good to think through this in this course from a single variable calculus perspective. Okay, in the next example, we use a law from physics. Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. Yeah, so the force on a spring is known to be the spring constant times x, which is the displacement from the equilibrium position. Okay, and so what's nice about this is it's naturally a force as a function of position, which lends itself to calculating the work done. And so they say here a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Okay, so if a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to length of 15 centimeters, then you can use this information to get the spring constant. Okay, and then now that you have the spring constant, you've got that force as a function of x, but you have to represent x is not just, x is the displacement from the unstretched position. So like when x is equal to 10, then the force is 0, or you could just you could say, like, what you would probably say is, so I don't know what they do, but you would say you're stretching x, you're going from f, say they get the spring constant here, k is equal to 800. And then what you would say is you do the integral to get the work done. You do the integral from x is equal to 5 to x is equal to 8, right? Because the force is equal to 0 when x is equal to 10. And that's what they do, you see, from going from 5 to 8. For 5, they convert it to meters. You have to keep the units in line, and you'll see in example problems how we make sure the units are lined up correctly. But they're talking about not the work done from the force on the spring, because that would be negative. Because if it's moving in this direction, it's going from 15 to 18, but the spring force is pulling in the opposite direction, then that's negative work. But they're talking about the work done from like you pulling on it. So you pulling on it, you're pulling in the same direction as the the block is moving, so the work is positive. If you were talking about what's the work of the spring force, then it would be negative. Okay, a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So this is a good example of how you can, just how integration is used in certain situations. Like you can always look at a problem and think, I could potentially integrate this. Or what I mean by that is I could potentially do an infinite sum on this. So let's take a look here at this in detail. All right, so again, it says a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So you have this 200-foot cable, or no, 200-pound cable. It's 100 feet long. So the whole cable, all 100 feet of it weighs 200 pounds. But you're pulling it in, right? How much work is required? So you can't just say 200 pounds times 100 feet. Why not? Because as you pull the cable in, there's less weight you're pulling up, right? When you've pulled in 50 feet of cable, then there's only 100 pounds of cable hanging. So how could you figure this out? Well, what you would think is, if I could break this down into pieces, then I could get the answer here. So in what way? How could you break this down into pieces? Well, the idea is, if you break this entire, so here's the 100-foot cable before you start pulling. You divide this up into pieces, and you're going to calculate the work done to lift each of those pieces to the top of the building and add those up. Okay, so for each piece, we haven't started yet, and we're going to break this up. We're going to divide this up into, let's say, 10 pieces, just to start, 10 pieces. Okay, we haven't started pulling the cable yet. So for each of those 10 pieces, what's the work done to pull that piece to the top of the building? Well, okay, it would, if you divide 200 divided by 100, you get 2 pounds per feet. All right, so in that case, 2 times the width of the delta x of those pieces, that's the weight of that piece, right? And then, so that's the weight of that piece. And then the work done to lift that piece to the top of the building is, we can think about it, with the x coordinate, it's the x coordinate of that piece from the top of the building, which would be, let's say, going from the top of the building to the midpoint of the interval. Does that make sense? Because that means that for that piece, you've pulled that weight of that piece that distance. In that case, that would account for the work done to lift the entire cable to the top of the building. But what you can think about is, let's make those pieces smaller and smaller. Let's make the number of pieces larger and larger. And so you can turn it into an integral in that case. What is the integral? It's 2 times the coordinate, 2x, right? You're integrating it from 0 to 100. You turn that, so 2x delta x, turn that into an integral, do the integration, okay? There's a perspective of how you can look at a problem and say, hey, I could potentially solve this using an infinite sum, using integration. All right. Last example, it says a tank has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. The density of water is 1,000 kilograms per cubic meter. All right, so what they're saying here, we've got this inverted cone with a height of 10 meters and a base radius of 4. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. So we want to take all of this water and move it to a height of 10 meters is what it's saying. What's the work done to move all of this water here to a height of 10 meters? Well, what you should see here, if you look at this problem, this is a perfect problem for integration. If we break this up into pieces along the height direction, then we can think about, so for each piece, what's the weight of water that's in that piece, right? If this is here's a piece. What's the weight of water in this piece? And then we multiply that weight by like the x coordinate from the top. Like we make this the origin, so whatever this x coordinate is, we multiply the weight of the water in the piece times the x coordinate, and that's going to give us the work required to move that water to the top. And we just integrate from x is equal to 2 to x is equal to 10, right? And so what they do is they have the coordinate, the origin here, and then so we go from 0 to 10. And so each of these pieces here, what's the weight of the water in each of those pieces? Well, we need the volume of this piece, so it's going to be pi times this radius squared. And so to get this radius, we have to get a function for how the radius of the cone changes with height, which we could do that. Pi times that radius squared times delta x, then times the density of water, 1,000 kilograms per cubic meter. That's the weight of the water in this piece, then times this xi star. And so they do all this. So here they get the radius function, the radius of the disk. Then they turn it into a volume, pi r squared delta x. Then they multiply that by the density of water. Oh, that gives the density of the water. Then they have to multiply it by the acceleration due to gravity to get the weight of the water. And then so here's the weight the weight of the water in that disk. Then they multiply that times the coordinate, which is from the top. That's the work done for that little disk of water. And so then you integrate. Then you want to sum all of those little disks from x is equal to 2 to x is equal to 10. You see? So we're going to work a bunch of example problems to illustrate this idea of you can just look at a problem, and it doesn't have to be something that the type of problem, an exact type of problem that you saw in the textbook, but you can still look at it and say, I can integrate this, right? You should be able to look at this here, this problem, and say, wow, yeah, this is definitely something I could do an infinite sum on. I could integrate to find this answer. That's a skill that we're trying to develop. And so this will be a good section. The example problems in this section will be helpful in developing this skill. So let's work some example problems.